Mass percent or percent composition is an element's percentage of a compound's total mass. So to find mass percent of an element, you take the mass of that element divided by the total mass of the compound, multiply by 100. So what is the mass percent of each element in calcium nitrate? First thing you got to do is add up the total mass of calcium nitrate. Calcium being 40.078, nitrogen being 14.007, and there's 2 nitrogens, oxygen being 16, and there are 6 oxygens. There's 2 nitrogens and 6 oxygens because that 2 outside the parentheses distributes. So my total mass of this compound is going to be 164.092 grams per mole, or AMU. It doesn't actually matter because units will end up canceling when we solve for percent anyway. So to find the percent of calcium, all I do is I take my mass of calcium in my compound, so 40.078, over my total, and multiply it by 100. There's not really sig figs with this. Sig figs come from measurement, and there was not really any measurements taken here. So we're just going to round to 2 decimals. So this one comes out to 24.42%. To find my percent of nitrogen, I do the same thing. I take the total mass of nitrogen in the compound. So that's the 14.007 times 2, so 28.014, over the total mass of the compound times 100. For this one is 17.07. And then percent of oxygen, mass of oxygen in the compound, over the total times 100 is 58.50%. When you add these up at the end, you don't have to add them up at the end, but it's a good way to check your work. They should come out to 100 or very, very close. This comes out to 99.99, probably just because of some rounding that I did somewhere. It is possible to get the percents to add up to 100 and still have the wrong answer, and that would happen if your total mass of your compound was incorrect. So it's probably a good idea to just double check that before you proceed with doing the problem in the future. Without doing any calculations, we're going to put the elements in C6H6O in order of decreasing mass percent composition. So we're just putting them in order. You don't need exact numbers. We can just kind of estimate. So carbon is about a mass of 12. There are 6 of them, so that's about 72 total. Hydrogen's about 1. There are 6 of them, so that's about 6 total. Oxygen is 16. There's 1, so that's 16 total. So very clearly, when you do that, you can see carbon is the highest, which immediately gets rid of B and C. And you can see that oxygen is the next highest because that's 16 out of the total. And so the answer there is A. And that's percent composition. Determining chemical formula from experimental data. So there are 2 types of formulas. There is the empirical formula and the molecular formula. The empirical formula is the simplest whole number ratio of atoms in a compound. So anytime we have formula units in ionic compound, that is an empirical formula. It's always the simplest whole number ratio. A molecular formula tells you the actual number of atoms of each element in a compound. So an empirical formula can be the same as a molecular formula. Let's say my molecular formula for propane is C3H8. So propane actually has 3 carbons and 8 hydrogens. That's also the simplest ratio. So that serves as both an empirical and a molecular formula. So we're going to write empirical formulas for the compounds represented by the molecular formulas. So again, all you're doing, lowest whole number ratio. So C4H8 can reduce to CH2. B2H6 can reduce to BH3. CCl4, there's only 1 carbon that can't reduce. So it's just CCl4. The empirical formula is the same as the molecular formula for that one. The empirical formula, again, is the simplest whole number ratio of the atoms or moles of elements in a compound. It is not a ratio of masses. You can actually calculate an empirical formula if you are given percent composition of the compound, or if you're given the masses of the elements formed when the compound decomposed or that react together to form a compound. So let's look at how to do that. If you are given percentages, you are going to convert your percentages to grams. You can do that because you assume that you would start with 100 grams of a compound. So if a compound's 30% oxygen and you have 100 grams of oxygen, or 100 grams of the compound, you would have 30 grams of oxygen. If it's already in grams, you skip that step. Then you'll convert grams to moles using the molar mass of each element. And then, actually don't do this step, you're going to divide by the smallest number of moles, because again, empirical formula is the smallest whole number ratio. So what you want to do is you want to get that ratio, and the way you get that ratio is dividing by the smallest number of moles. If the result is within a tenth of a whole number, you can round to the whole number. If it is not within a tenth of a whole number, you need to multiply to get to a whole number. So for example, if the ratio is 0.5, you'd multiply all by 2. If the ratio is 0.33 or 0.67, those are thirds, so you'd multiply by 3, so on and so forth. So we're going to follow those steps as we solve this problem here. I have 30.5% nitrogen, so we're going to convert that, or we're just going to pretend it's grams, so 30.5 grams of nitrogen. I'm going to convert that to moles. So nitrogen is about 14.01 grams per mole. I have 69.5% oxygen, so I'm going to say it's 65.9 grams of oxygen. Oxygen has a molar mass of 16 grams and 1 mole. Oxygen and nitrogen are both diatomic, but diatomics are only diatomic when they are by themselves. So because these are part of a compound, they are not diatomic. You don't double the mass, you just use the mass of a single atom. So for nitrogen, I'm going to get 2.17706. Now it's really, really, really important at this step that you do not do sig figs. It's not something I usually say, but do not do sig figs at this step. Go to 4 or 5 decimal places. For this one, and the unit of that, of course, is mole nitrogen. For oxygen, I get 4.34375 mole oxygen. So now what I want to do is I want to get the ratio of nitrogen to oxygen. And it's easier if that ratio is a whole number. So what I'm going to do is I'm going to divide all mole amounts by the smallest mole amount. So I'm going to divide both of these numbers by nitrogen's mole amount. Obviously, that would give you 1 nitrogen. Dividing by 2.17706, this is going to give you 2 oxygen. So the ratio in this compound is 1 nitrogen to 2 oxygen, and so you would write your formula as NO2. Your empirical formula for this compound is NO2. I have a 0.3546 gram sample of vanadium metal being heated, so it's reacting with oxygen. To reach a final mass of 0.630 grams, I need to calculate the empirical formula. So this is incorporating the law of conservation of mass, really. We know we have the vanadium. It's reacting with the oxygen. It's forming some vanadium oxide, and the actual formulas don't really matter because I just need to know amounts. So 3.456 grams of vanadium, and then at the end, my total is 0.6330 grams of my compound. So we subtract those to get 0.2784 grams of oxygen that reacted. So the way the law of conservation of mass works is if I started my reaction with 0.3546 grams of vanadium, I end my reaction with 0.3546 grams of vanadium. So I can use those masses of the reactants as the masses of the elements in the empirical formula of this vanadium oxide. So 0.3546 grams of vanadium. Vanadium has a molar mass of 50.942 grams per mole. I have 0.2784 grams of oxygen, which has a molar mass of 16 grams per mole. So this is going to give me 0.0069609. Remember, you want to go to a lot of decimal points at this point. This will give me 0.0174. So that's mole of V. That's mole of O. To get your formula, again, you need to divide by the smallest to get the lowest ratio. So my smallest number is obviously the 0.0069609. That'll give me 1 vanadium. When I divide the oxygen, I get 2.499, which is very, very close to 2.5. You can't round it to a whole number because it is not within a tenth of a whole number, but we can round it to 2.5. So what I have to do at that point, that basically says my ratio is VO 2.5, 1V to 2.5 oxygens, but empirical formulas are lowest whole number ratios. So to get that to a whole number, we multiply the whole thing by 2. And my final answer for my empirical formula is V2O5. Molecular formulas are a whole number multiple of the empirical formula. To determine the molecular formula, you need to know the empirical formula and the molar mass of the compound, the molar mass of the molecular formula of the compound. So the molecular formula is whatever the empirical formula is times n, where n is a positive integer, a whole number. You solve for n by taking the molar mass of the compound and dividing it by the empirical formula molar mass and rounding that to a whole number. You might not get exactly 2, but if you get 1.99, you can round it to 2. And it should be, again, within a tenth. If it's not within a tenth, probably there was some kind of mistake that you made in your calculations. You should go back and check your calculations. So if I am given the empirical formula and I am given the molar mass, I can solve for the molecular formula. You will always be given the molar mass in these problems. You will have to be given the molar mass of these problems. So what I do is I take the empirical formula, C2H3O, and I add up the mass of the molecular formula. So C2H3O has a mass of 43.05. Then I'm going to take the molar mass over the empirical formula mass that I just solved for. So the molar mass is what was given in the compound, or I'm sorry, given in the problem. The empirical formula mass is what I just solved for. So that's going to be 86.09 over 43.05. And that's going to give you about 2. Not exactly 2, but very, very, very close to 2. So then I take my empirical formula and I multiply it by that integer that I just solved for. So that 2 becomes what I multiply my empirical formula by. And so my molecular formula is C4H6O2. My molecular formula is the empirical formula times that number that I solved for. And molecular formulas should not be in the lowest whole number ratio. Sometimes you will be given a percent composition, and then you will be asked to determine the empirical formula and the molecular formula. So we do the process for finding the empirical formula. First, we take the percent, 65.45. We take the percent, change it to grams, and then convert it to moles for each atom. So 5.492 grams of hydrogen, 1.01 grams in 1 mole of hydrogen. Don't know why I wrote a K. And then 29.06 grams oxygen times 16 grams oxygen in 1 mole of oxygen. So here I will get 5.4496. Again, remember this step, do not go to sig figs, go to 3, 4, or 5, probably even better, decimal places. This is 5.4376. This is 1.81625. And then to get my ratio, because remember that's what an empirical formula is the lowest whole number ratio. To get my ratio of the elements in my formula, I'm going to divide everything by my smallest mole amount. So that would be 1 oxygen. This comes out very, very close to 3 hydrogens. And then this comes out to very close to 3 carbons. So my empirical formula, the first thing that it's asking for, is C3H3O. To solve for my molecular formula, I'm going to add up the mass, 3 carbons, 3 hydrogens, and 1 oxygen. And I'm going to get a mass of 55.06. Then I will take my molar mass over my empirical formula mass. So I'm going to do the molar mass that was given to me, 110, over my empirical formula mass that I just added up, and that gives me about 2. So I'll take my empirical formula and multiply it by that number that I just solved for. So my molecular formula is going to be C6H6O2.